Ice doesn't care about water. You pour water on ice, it cracks. Sharp, loud, violent. You've heard it 1,000 times. Drop ice cubes in a glass of room temperature water and listen. That sound. But why? Why does ice break when it touches its own liquid form? You'd think they'd get along. Same molecule, same H2O. But they don't. They shatter. Most people have never really thought about this. You just accept it. Ice cracks. That's what ice does. But that's not an answer. That's just repeating what you observed. When you really ask why, when you dig into what's actually happening in those microseconds between water touching ice and ice fracturing into pieces, you discover something so fundamental, it changes how you see every solid object around you. Feynman loved this kind of question, the simple ones, the ones hiding in plain sight. And once you understand it, you'll never pour a drink the same way again. Let's start with something simple, something everyone knows. Things expand when they get hot. Heat up metal, it gets bigger. Cool it down, it shrinks. You've seen this. Railroad tracks have gaps. Bridges have expansion joints. Your car's engine has precise tolerances because metal expands. This is basic. Thermometers work on this principle. Mercury expands, climbs up the tube, shows you temperature. Everyone learns this. Now think about ice. Frozen water, solid, crystalline structure. You pull it out of the freezer, minus 18 degrees Celsius. That's 0 Fahrenheit. Standard freezer temperature, the ice is cold. Every molecule locked in place. Hydrogen bonds holding them in a specific geometric arrangement. Hexagonal lattice, beautiful structure, stable. Then you pour water on it, room temperature water, 20 degrees Celsius. That's 68 Fahrenheit. You just created a temperature difference of 38 degrees Celsius in less than 1 second. Here's the thing. That temperature difference doesn't spread evenly through the ice. It can't. Heat moves at a specific rate through materials. It conducts, flows from hot to cold, but it takes time. The surface of the ice, the part touching the water, tries to warm up instantly. The molecules there start moving faster. They want to expand. They need more space. But the molecules 1 millimeter deeper into the ice, they're still frozen solid, still locked at minus 18 degrees. They haven't gotten the message yet. Now watch what happens. The surface expands. The interior stays the same size. You've created stress, enormous stress. The surface is pulling away from the core, trying to grow while being anchored to something that refuses to move. Something has to give. The ice cracks, it fractures, splits apart. That sound you hear is the sound of a material failing under stress. It can't distribute fast enough. Let me show you what I mean with numbers. Real measurements. Ice has a thermal expansion coefficient. When you heat ice by 1 degree Celsius, it expands by about 51 millionths of its original length. That's 51 x 10�6 per degree. Sounds tiny. It's not. When you hit it with a 38 degree temperature jump on the surface while the interior stays frozen, you're trying to make the surface expand by about 0.2%, while the core expands 0%. The surface wants to be 2 millimeters longer for every meter of ice. The core says no. Think about it. You're pulling the surface away from itself, creating tension. And ice isn't flexible, it's brittle. Crystalline solids are. They don't bend, they don't yield, they crack. The stress builds up faster than the material can redistribute it. Faster than the heat can conduct inward. The result is fracture. Clean, sharp, sudden fracture. But wait. Let me say that differently because this is important. The problem isn't the temperature change itself. The problem is the gradient, the difference between surface and interior happening too fast. If you warm the ice slowly, uniformly, it would be fine. Put ice in a room, let it warm up over hours, it doesn't crack, it just melts eventually. But pour water on it, create a massive temperature gradient in microseconds, it shatters. And here's where it gets strange. Different materials handle this differently. Pour hot water on metal, it might be fine. Metal conducts heat fast, really fast. Copper conducts heat about 500 times faster than ice. So the temperature equalizes quickly. The gradient doesn't build up as intensely. The stress distributes. But ice? Ice conducts heat slowly, very slowly, about 2 watts per meter Kelvin. That's roughly 4 times slower than concrete, so the heat just sits at the surface. Trapped. Building stress. Breaking bonds. Let's go back to the molecular level. Let me take you down to where this actually happens. Ice is water molecules locked in a hexagonal crystal structure, each molecule connected to 4 others through hydrogen bonds. These bonds are specific, directional. They hold the molecules at precise angles, roughly 109.5 degrees. This creates the crystalline lattice. Now, when you heat the surface molecules, they start vibrating more, moving faster. They need more space, but they're still connected to their neighbors, still bonded. They pull on those bonds, stretch them. The bonds resist. They have strength, but they have limits. The stress on those bonds depends on how much the molecules want to move versus how much they're being held back. It's measured in pascals. Pressure, force per area. Ice can handle about 1 to 3 megapascals of tensile stress before fracturing. That's about 150 to 450 pounds per square inch. When you create that temperature gradient, surface expanding while interior stays fixed, you can easily exceed this. The bonds break, the crystal fractures, the crack propagates. One broken bond leads to the next. Chain reaction, milliseconds. Done. Now here's the beautiful part. This isn't just theoretical. We've tested this over and over. You can measure the thermal stress precisely. Engineers do this all the time. They call it thermal shock. It's a massive problem in materials science. Ceramics crack in the oven for the same reason. Glass shatters when you pour hot liquid in cold glass. Pyrex was invented specifically to resist this by lowering the thermal expansion coefficient. Borosilicate glass expands about 3 times less than regular glass. Less expansion means less stress, means less cracking. You can calculate exactly when a material will crack from thermal shock. There's an equation. The thermal stress equals the elastic modulus times the thermal expansion coefficient times the temperature change times a geometric factor. For ice getting hit with room temperature water, the math says fracture is almost guaranteed. The numbers don't lie. Young's modulus for ice is about 9 gigapascals. Multiply by the expansion coefficient, multiply by the temperature gradient, you get stress levels well above the fracture threshold. It has to crack, and this has been known for a long time. Not specifically for ice in drinks, but the principle. In 1870, a German physicist named Gustav Zeuner worked out the mathematics of thermal stress in materials. He was studying steam engines, trying to figure out why metal parts kept cracking. He realized it was the rapid temperature changes, the gradients. Since then, every engineering student learns about thermal shock. It's fundamental, it's unavoidable. It's why spacecraft need heat shields that ablate, carrying heat away before it can conduct deep into the structure. It's why you can't take a glass dish from freezer to oven. It's why ice cracks in your drink. But there's more. Ice is special. Water is weird. Most materials contract when they freeze. They get denser. Molecules pack tighter in the solid state than the liquid state. Makes sense. Less energy, less movement, closer together. But water expands when it freezes. Ice is less dense than liquid water. That's why ice floats. That hexagonal crystal structure with those specific hydrogen bond angles creates more space between molecules than liquid water has, about 9% more volume for the same mass. This matters for the cracking. When ice starts to melt at the surface, when those surface molecules transition from solid to liquid, they actually want to contract, take up less space, but they're attached to frozen ice below that's still in the expanded crystalline state. So you get stress from two sources: the thermal expansion from temperature change and the phase transition trying to happen at different rates through the material. Double trouble. Both create stress gradients. Both contribute to fracture. Let me show you how fast this happens. Heat conducts through ice at about 1 millimeter per second for these temperature ranges. That's the thermal diffusion rate. So in the first second after pouring water, only the top millimeter or so warms significantly. That creates a 1 millimeter thick layer trying to expand while everything beneath stays frozen. The stress is concentrated in that thin surface layer. Concentrated stress means higher peak values. Higher peak values mean easier fracture. The crack initiates at the surface, right where the stress is highest, and propagates inward along crystal planes. And here's something Feynman would love. You can hear which way the crack is going. The sound of ice cracking isn't random, it's information. High-frequency cracks mean small surface fractures. Lower frequency pops mean deeper cracks propagating through the bulk. The frequency tells you the size of the fracture event. The timing tells you the propagation speed. Those cracks move at about 3,000 meters per second through ice, about 1/5 the speed of sound in ice. Fast enough that the whole cube fractures before the heat penetrates more than a few millimeters deep. Now watch what happens over the next few seconds. The cracks have released the stress, broken the ice into smaller pieces. Each piece now has more surface area. More surface means faster heat transfer. The pieces melt faster, but it also means each piece can expand more independently. Less constraint, less stress buildup. That's why you typically hear multiple cracks in the first second or two, then it stops. The material has broken itself into pieces small enough that thermal stress can be accommodated without further fracture. Think about it. The ice solves its own problem by breaking. It's not trying to do this. There's no intelligence. It's just physics. Stress succeeds strength, material fails, stress releases equilibrium. But it looks purposeful. Pour water, here cracks, they stop. System stabilizes. The final state is thermodynamically favorable. Smaller pieces in thermal equilibrium with the liquid. No more stress gradients, no more cracking, and this pattern shows up everywhere once you know to look for it. Cracked pottery from uneven kiln cooling. Tempered glass that shatters into small pieces because surface and interior have different stress states built in during manufacturing. The way rocks split apart in forest fires. The way concrete cracks in freeze-thaw cycles. The way old phone screens shattered when you dropped them because the glass couldn't handle the stress gradient from sudden impact. All the same fundamental physics. Stress gradients exceeding material strength. Fracture as the stress relief mechanism. But let's bring this all together. Why does ice crack when you pour water on it? Because ice is a brittle, crystalline solid with low thermal conductivity and a relatively high thermal expansion coefficient. When you create a sudden temperature gradient by pouring room temperature water on frozen ice, the surface tries to expand while the interior remains dimensionally stable. This creates tensile stress at the surface and within the crystal structure. The stress exceeds ice's tensile strength of about 1 to 3 megapascals. The crystalline lattice fractures along planes of weakness. The crack propagates at about 3,000 meters per second. You hear it as a sharp crack or series of cracks. The fracture creates smaller pieces with more surface area and independent expansion capability. The cracking stops when the stress gradients equalize below the fracture threshold. That's the complete answer. Not thermal shock as a magic phrase, not because temperature difference as a vague gesture, the actual mechanism, the actual numbers, the actual material properties and stress calculations and fracture mechanics. This is how materials work. This is how reality works when you look closely enough. And here's the deeper truth. Every solid object around you is held together by electromagnetic forces between atoms and molecules. Those forces have specific strengths. When you apply stress, external forces pulling atoms apart or pushing them together, you're fighting those electromagnetic bonds. Push hard enough, fast enough, asymmetrically enough, the bonds break, the material fails. Sometimes that failure is ductile, material stretches and flows. Sometimes it's brittle, material cracks and shatters. Ice is brittle. The temperature gradient from water creates the stress. The crack is inevitable. Feynman spent his career teaching people to ask the next question. Don't stop at thermal shock. Ask why thermal shock breaks things. Don't stop at stress. Ask how much stress and compare to what strength. Don't stop at temperature change. Ask how fast, through what material, creating what gradient. Keep asking until you hit bedrock, until you reach fundamental principles, forces, bonds, structures, numbers. The sound of ice cracking in your glass isn't just ice cracking, it's the sound of a material reaching its fundamental limit. The sound of electromagnetic bonds breaking because thermal stress exceeded molecular binding energy. The sound of atoms being pulled apart faster than thermal energy can redistribute. The sound of physics working exactly as it must. Not approximately, not sort of, exactly. And this process, this cascade from observation to question to mechanism to mathematics to fundamental forces, that's how science works. That's how you understand anything deeply. You don't memorize that ice cracks. You understand why it must crack, why it can't do anything else given its material properties and the stress state you created. You move from memorizing facts to seeing the underlying reality. So the next time you pour water on ice and hear that crack, you're not just hearing ice break. You're hearing the universe doing mathematics, calculating stress fields and comparing them to bond strengths and executing fracture mechanics in real time. Every crack is a solution to an equation. Every sound is data. The ice is teaching you about crystalline structures and thermal gradients and material failure if you know how to listen. That's what Feynman understood. The world is comprehensible, not comfortable, not simple, but comprehensible. You can understand why ice cracks, really understand it, down to forces and structures and numbers. And when you do, when you really see the mechanism, the world becomes more beautiful, not less, more mysterious, not less. because now you know there's an answer, a real answer, and you know how to find it.